So for this last example, all that we're going to look at is how to actually solve this system of equations in MATLAB. And I'm going to show you a new way to solve it that we haven't looked at beforehand. So last time that you worked in MATLAB to solve a system of equations like this, you looked at Cramer's rule. And we're going to just do it an easier way than Cramer's rule. The reason we do Cramer's rule is to show you how to do it by hand, and then you verify that in MATLAB. But the solution is actually much simpler than if you don't use Cramer's rule in MATLAB. So all that we need to do is step one. We actually need to define our coefficient matrix, which we'll call A. Remember that the way you enter a matrix into MATLAB is to give it a variable name, set that variable equal to, use a square bracket to tell MATLAB that you're going to enter an actual matrix, and then put the elements of the first row. Start with the element in the upper left-hand corner, -1. Since we're moving in a new row, we'll separate that by a comma. Then we'll have the element in the second column, which is 0.866. Since we're going to go to a new row, we'll use a semicolon, and within the new row, we'll start over in the first column. We have the entry 0, and in the second column, we have the entry 0.5. And we'll close that bracket to tell MATLAB we're done defining A. The only other vector we're going to need is the constant vector B. Now remember that this is a column vector, so when we enter it, we're going to separate each element by an actual semicolon because each time we're going to a new row. So we'll start with 0, and then we'll actually put the values of the mass and the acceleration due to gravity in now. We need to take the mass, which was 40 kilograms, and we'll need to multiply by 9.81 meters per second squared. And remember, in MATLAB, we're actually going to have to enter an asterisk there because MATLAB doesn't know what we mean when we just type two numbers next to one another. So I'm going to choose to actually open a new script just to store all of this in. So I'll click on the new button. I'll begin by, and I'll put a comment to show what I'm doing. I'll say I'm going to define my coefficient matrix. So I'll say that A is equal to, and I'll enter the values, -1, comma, 0.866, semicolon, 0, 0.5. And usually it's good practice, I think, whenever you're entering or writing code to save it. Maybe you call this like lab4 as an M file. And then every time you define a variable, actually run your script and make sure it works like you're thinking. So if you have stuff on your MATLAB command window, CLC will clear it for you. And then if you just run the script, we should see that initially we get the matrix A defined as we want. In element 1, we have -1. In element 1, 2, 0.866. Element 2, 1, 0. Element 2, 2, 0.5. And then what I'm going to do is actually, and I should put a comment to make my code readable, I'll define my constant vector. And how I'm going to do that is I'm going to define B. I'm going to make the first element 0. I'll use a semicolon to go to a new row. And then I'm going to put in the 40 times the 9.81. And if you like, you can actually separate out that calculation. That's no problem. But I think that it's just efficient to let MATLAB do the work for you. Actually, if it were me, I wouldn't even have 0.866 and 0.5 in here. I would have cosine of 30 and sine of 30. So I'm going to put a semicolon after A because I know A works. I don't want to see it anymore. I'm going to save my script. Easiest way to do that is Control S. And then I will execute this again and hope that B gives me a column vector, which it does. And you can do the math in your head. If something's got 40 kilograms of mass, remember that 9.81, that's a very precise number, but you can just round it off as 10. So it should have about 400 newtons of force. So something that's got 40 kilograms of mass should have about 400 newtons of weight in the downward direction. So here's the part that you don't know yet, is how do you actually solve for the unknown vector here? Well, the way that we're going to do that, and this is going to look funny here, but I'm going to say that the tensions, and they're going to be a vector, is going to be A, and then actually, rather than doing a forward slash, do a backslash. So usually on most keyboards, it's directly above your actual enter key. And just type A and B with the backslash in between. And if you notice, that kind of looks like division, and that's exactly what you're doing. And this is the best way to actually solve a system of equations in MATLAB. And if you want some amusement, you can actually go to Google and look up a MATLAB t-shirt. This is something that you see on t-shirts that people wear for MATLAB. It has to do with this matrix vector division operation. So if I save my script, and I don't want to put a semicolon there because I want to actually see what my results are, and I will run here, there I actually see what my tensions are. So I'm just going to copy those over to my .chem. What that is telling me is that the tension in cable AD is about 680. I'm going to round it to 3 significant figures. You can do it however you want. The point of this lecture isn't rounding. It's just to walk you through this process. 680 newtons. And TAC, or TAB, I should say, the tension in cable AB is going to be 785 newtons. So from an engineering point of view, you just did all that analysis, but what's the point? Well, if you were asked to actually assemble this for someone and they asked you, oh, hey, make sure that you pick cable that can adequately support this load, what you would need to ensure is that the tensile strength of the cable that you use for the connection point between A to D, you have to make sure it can at least bear 680 newtons of tensile force. And then TAB, the cable that's going this way, it has to be able to withstand at least 785 newtons of tension. Since you probably wouldn't buy a separate cable for both connections, you probably would let this actual quantity serve as the deciding factor in your cable choice. And you probably wouldn't want to just go to whoever you're going to buy your cable from and say, hey, I need cable that's strong enough to withstand 785 newtons of force. You probably wouldn't even want to do 800. You probably would want to add on a little bit of a safety factor in there as well. So that's where it kind of starts to transition from the engineer that's doing the analysis and applying mathematics and physics in order to solve for quantities that guide their decisions to actually making the engineering decisions, deciding what your safety factor needs to be, thinking about the most efficient way to actually build something that is capable not only of doing the job, but meeting those all the requirements of the end customer. So hopefully you found this lecture interesting. It allowed you to apply a lot of different concepts that we talked about so far. It is a lab technically, but I'm calling it a lecture because the majority of the things you actually were done for you as long as you watch through this. So all that I want for the last step 4 is for you to actually hit print screen and take a screenshot of this and paste it into your assignment. So have a good weekend. Hopefully you had a good time getting caught up on stuff this week, and I will talk to you all soon. This will be due next Sunday. So if you see this posted and you freak out that it's actually due in a couple of days, the actual submission is not due until next Sunday.